Welcome to Unit 7, Trigonometric Functions, Lesson 1, Graphing Sine and Cosine Functions. You should be familiar with the sine and cosine functions. You should have worked with them a lot throughout your math career. Now we're going to talk about how their graphs look and how do we graph them, including doing the transformations that we learned earlier in the year. So sine and cosine are functions that are called periodic functions. And what that means is that they have repeating values and therefore their graph kind of looks like a wave. So a sine graph is a graph of the function y equals sine theta. You can also describe the sine graph as a sinusoidal graph. So a periodic function is a function that repeats itself over regular intervals or cycles of its domain. We have a general formula for it. Now, I just wanted you to notice that this general formula has y equals a sine b x minus c plus d. And this should look familiar to you. It's extremely similar to the transformations that we've done previously in this course. So a represents our amplitude, that's our vertical stretch. B is the number of cycles in 360 degrees or 2 pi. It just depends if you're measuring in radians or degrees. C is our horizontal shift. That's equivalent to your h value if you remember that general transformation formula. And D is our vertical shift, or equivalent to k. So this should be really familiar to you. You've seen it already. You've mastered it. All that we're replacing now is a trigonometric function inside of it. We'll just finish defining the terms that were provided. The first one is period. The period is the length of the interval of the domain over which a graph repeats itself. And we have two sort of ways we can figure that out. We can figure out the value for b, which fills into this formula that we have up here, b. We can figure that out by going 360 divided by b, or 2 pi divided by the absolute value of b. Depends on the domain that the question is asking you for. If it's given in degrees, then use this one. If it's given in radians, use this one. We can also solve for b by going 360 divided by the number of periods given between 0 and 360, or 0 and 2 pi. We have the general term sinusoidal curve. This is the name given to a curve that fluctuates back and forth like a sine graph, and it oscillates repeatedly up and down from a center line. So if we look at this sample graph here, we would have a center line obviously going straight right through it. The trigonometric functions are also sometimes called circular functions because they're based on the unit circle. So these values correspond to a value on the unit circle, and that's how these two topics are related. We also have amplitude, which is the maximum vertical distance the graph stretches, either on top of or below the central axis of the curve. And we'll also have a median line in all sinusoidal functions. So it's our y equals sine x plus d, where d is the median, and it's just representing that middle line. For example, in this one, it's 0. You typically will always get a positive value for that because the function is fluctuating about one specific horizontal line, and typically the value here, positive, cancels out the value here, negative. On the second page, you have two examples of the y equals sine theta and y equals cos theta with a corresponding unit circle to give you an idea where we get some of these values from. Now, there's some characteristics that you need to recognize to figure out whether you have a sine graph or a cosine graph. Sine graphs, if there's no transformations done to them, they typically go right through the origin, 0, 0. Whereas cosine graphs, they'll go through 0, 1. And if you punch that into your calculator, the cosine of 0 or the sine of 0, you will get that result coming back out to you from your calculator. Over 2 pi, they typically have this same shape, and then those manipulations on A, B, C, and D are what changes the shape of the graph. So if we just have y equals sine theta and cos theta, you're always going to have this general shape. From 0 to 2 pi, the sine graph will look like that. And from 0 to 2 pi, the cosine graph will look like that, kind of like a valley. I put an interesting fact over here. We talked about it in class briefly, how back in the day before we had calculators, we would use the sine and cosine tables to do that. And there was actually a fact in the textbook about the Indo-Asian mathematician Aryabhata from 476 to 550. So 1500 years ago, he created those tables, which I think is really, really exceptional if you think about the technology during that time. So thank you to him. Now our calculators do it for us. So the next thing is just an example of sine theta from 0 to 360 or from 0 to 2 pi. Notice that the shape of the graph is exactly the same. Nothing changes. All that changes is degrees or radians as your intersection points to help you to graph. But the graph of y equals sine theta has some characteristics. So the characteristics are the curve is periodic and it's continuous. So it continues off into infinity. If we kept plotting points, it would just carry on infinitely in both directions. But we're given a domain and restrictions on our domain here, so you just keep it within those x values. The minimum value of the graph is -1. The maximum value is +1. The domain is theta, any real number. The range is -1 to +1. Maximum is +1. The amplitude of the curve, so you're just measuring from here down to the central line. So from the highest point down to the median is 1 unit in height. The period, so the period is how many times it repeats itself between 0 and 2 pi. So we have 1 unit of sine from 0 to 2 pi or 0 to 360. The y-intercept is 0. And then you're given the general intercepts where the sine graph will cross the x-axis. The general formula for it would be 180n. So every 180 degrees or pi, the sine graph will cross the x-axis. But as long as you recognize it and plot it properly, it will be fine. Now in this example, I ask you to sketch the graph of y equals cos theta. You have an example of it on the previous page, so it shouldn't be too hard to do. But if we mark this as 1 unit, we will have a point at 0, 1. I apologize, this graph paper is a little bit fuzzy, but I think you get the gist of it. You'll have a maximum at 0, 1, as well as at 360 degrees and 1. Okay, and we'll have our minimum value at 180 degrees and -1. So just like the sine graph, the y values fluctuate within +1, -1. And if you think back to your unit circle unit, that corresponds to those +1, -1 values on the unit circle. So this is where the two connect. Now, we have some characteristics of this graph as well. The domain, theta can equal any real number. The range, of course, is -1 to +1. Max and min are plus and -1 as well. Our y-intercept, it's a little bit different than our sine graph. Typically, if there's no transformations done to the cosine graph, it's going to go through the point 0, 1. It will have x-intercepts at 90 and 270 for the restricted domain that we're given, 0 to 360. And of course, we'll repeat every 180 degrees. The amplitude is 1. That's just the height from here to here. And the period is 360 degrees. So the amplitude, this is where it should look familiar to you, where we have those a and b values. The amplitude of the function is associated with the vertical stretch. So that's your a value here, here, and here. Doesn't matter which function you have behind it. The period is associated with the horizontal stretch. So that's your b value, and you should be familiar with that already. Our next thing that we want to be able to do is to determine the amplitude of a sine function or a cosine function. So all we're looking for here is the height of half of it. Okay, so if we have our regular, there's a lot of things going on this graph. It's been plotted y equals sine x, y equals 0.5 sine x, 3 sine x and negative 2 sine x. So remember that that negative 2 would just be a flip over the x-axis to give you negative y values. Now, the amplitude, it's really easy to find. You're essentially just looking for the central line. In this case, it's 0. There's no horizontal or vertical shifts. So in this case, it's 0. You just see how many units tall half the curve is. It's 3. But another way you can do it mathematically is to just take the max and min values of the graph that you're given and divide them by 2. As you can see, it comes out to the exact same height that you're dealing with. So this is the mathematical way to do it, or you can just pull it off of the graph by counting the units tall of 1/2 of a period of the graph. In the bottom here, there's a comparison of the graphs in relation to the y equals sine x graph. You can just look that over yourselves and see where the differences are. Notice how the restrictions on the changes. Notice how the changes to the a value affect the range that's given at the end. The other thing we want to be able to do is to determine the value of b, or the period of the sine function. So we are asked here to sketch the function sine y equals sine of 4x over 0 to 360 degrees. So notice that this means that we're going to have 4 repetitions of that curve. On this graph, we've graphed y equals sine x. That's a beautiful sinusoidal curve right there. And then notice that repeating it 4 times within that same 360 degrees gives us 1, 2, 3, 4 bumps. Okay? It's really simple and straightforward. Because it's in degrees, you're just going to take the 360 degrees divided by the number of times that curve repeats itself in the same domain. So I just want to highlight for you that when we're talking about one period of the graph, we're talking about 1 sine x. So from here to here, once we cross this 0 at 90 degrees, we're getting a graph that looks exactly the same as this first section here. So how many times does this section repeat itself between 0 and 360 degrees? That's what this question is asking. So you can see it repeats itself 1, 2, 3, 4 times, and our period becomes 90 degrees. In example B, we're given a bit of a bigger domain, 0 to 4 pi. Notice how having a fraction in that b location really spreads the graph out. So remember when we were finding b in those transformations that whatever you're doing with the b value, you're flipping it and dividing. So you're dividing by 1/2, which means you're multiplying by 2. So the period of this graph is 4 pi. Okay, there's only one repetition from 0 to 4 pi. So that's how you solve for and calculate the period of a sine function. It's really simple and straightforward. Don't overthink it. Just be conscious of whether your graph is stated in degrees or radians and use the appropriate value on top. Other than that, to calculate the period, all you have to be able to do is count how many times a pattern repeats itself. Example 3, I've provided the correct answers here. You can just look at the characteristics that are provided for the graph. So here in A, 3 represents a vertical stretch of 3 units. Notice that it goes up to +3, and it's the only graph that hits +3. So that's a good hint to you that A is corresponding to that graph right there. This graph here, D, why do we know it's negative cosine x? Well, positive cosine x goes through +1, and this one's going through -1, and it's also got a peak at positive pi or pi radians away from the origin, and that's a good indication that you're dealing with the cosine function. This one's the only one that goes through the origin directly, so that gives you a good hint that it's the sine function. And the cos 3x, you can see in one period from 0 to 2 pi, we have 1, 2, 3 repetitions. So that matches with B. In part 4, you're given two graphs. You just want to determine the amplitude. So here we're just looking at the distance from here to here, which is 5. And that will give you your amplitude. On this graph, it's 4. It's going from the top maximum up to the median line. It's 4 units. The period, it ended up a bit weird in this one. It's only repeated 1.5 times. So the graph is stated in radians, 2 pi. So we're going to use the 2 pi over b to calculate the period. I guess this would be equivalent to 4 pi over 3. Of course it would, because if we multiplied this by 2, that's what it would give us. So wherever you ended up in this answer, that's fine by me. 4 pi over 3 is probably the cleanest answer because we don't typically want a fraction in the bottom there. So notice that in this graph, it goes from here to here. There's 1.5, and then we hit 2 pi. So 1.5 on the bottom. And then just fix it up to suit your needs. If you divided them out and got 1.3, that's okay. If you recognize that it needed to be 4 pi over 3 for the period, that's okay too. Here the period is 2 pi over 3. So you just want to count how many times it repeats. It's 1, 2, 3 times. So 2 pi over the number of repetitions, 3, will give you the period for that function. Don't overthink this. It's really that simple. It's just counting and matching with the graph. And finally, our last example, represent at least one cycle of y equals -3 cos 2x. Remember, a affects the y values and b affects the x values. Determine all that stuff it asks for there. So the amplitude of this is -3. So you want to recognize that because it's the cosine function, we're going to have a y-intercept at 0, -3. The period of the cosine function is pi. And the reason why is because we have a 2 value there. So instead of it going up to 2 pi, it's going to only go to pi. Max and min at plus and minus 3. We talked about y-intercept already. The x-intercepts are those listed there. The general format for it is pi over 4 plus pi over 2n, where n is any integer. So you can get results going all the way to positive and negative infinity. The domain of the function is x is any real number, and the range of the function is -3 to +3. So beyond this, you have some practice questions. You can just draw on your own increments for whatever suits the graph. So this one, it's got an amplitude of 6. You can just generalize it and draw it the best that you can. And once you're done the practice questions, you can move on to the homework for this lesson.